Okay, so very good morning to all the participants here. Uh, First of all, I'm very much grateful to Sri Ramchandra Engineering College, Pune, for providing me this opportunity to present my share of knowledge to all of you people. Also, I sincerely appreciate the efforts of Professor Bharti Misal for conducting this event. What I want to stress on today is the importance of earthquakes. I would start with an introduction to earthquake and I would slowly proceed to structural dynamics. I suppose a lot of the participants are new to this discipline. So I would make it as I would start from as basics as possible and slowly I would proceed towards the a little more advanced version of that. I would request everybody of you to stop me, interrupt me anywhere you like, uh, in case you do have any questions. Bharti, still I'm getting some admit requests. Should we wait or can I proceed?
No, you can add one and you can proceed.
Okay, okay, fine, fine.
Actually, HOD Nikam sir has joined now only.
Okay. Good morning, sir.
Welcome you, sir. Good morning.
Thank you, sir.
Good morning, sir. Good morning.
Good morning. Okay. So, Bharti, I'll resume it. Okay. So I'm audible now.
Okay, yeah, sure.
Yeah. This is the title for the topic for today, Introduction to Earthquake and Structural Dynamics. Myself, a research scholar in IIT Roorkee. I'm getting an admit request again. Okay. Yeah. So, we would see that earthquakes are one of the most deadly natural disasters that mankind has ever seen. On the left of this picture of the slide, we see some devastating and really disheartening images of the Nepal earthquake, right? So this is really not fair on humans to die such a devastating death, right? An earthquake is an event which occurs without a warning. So that's why considering earthquakes is of paramount importance. It's a disaster that can take lives within seconds, that too without any warning. That is why earthquakes are so important. And being in India, India is a country which is very much seismically active because of the convergence of the Indian plate with the Eurasian plate, and we have had a lot of devastating earthquakes since time immemorial, right? Basically, we are earthquake engineers. Earthquake engineering is basically an offshoot of civil engineers where we deal with loads which are dynamic, which vary with time, right? As earthquake engineers, our motto is our tagline is earthquakes don't kill, but buildings do. It's an earthquake that don't cause any death, but it's a building, basically improperly engineered buildings, which does all those devastation, right? Okay, earthquakes don't kill, but buildings do. That's the motto of, that's the tagline of earthquake engineers. Now, I would want to present some important terminology. Like we have a subject called seismology. Seismology is a branch of science which deals with the internal structure of the earth, right? As well as the origin, propagation, and penetration of seismic waves across various strata of the earth, right? So that is what seismology. And earthquake engineering comes when the seismic waves hit the ground and we model the building or design the building so as to limit the devastation caused by the earthquake. Now, let's delve into the structure of the earth. This is the globe, and when we cut open the surface of the earth, cut open the body of the earth, we find that the earth is composed of different layers, right? We have core, we have crust, we have mantle, and we have core. Core is further divided into inner core and outer core, and mantle is divided into lower mantle and upper mantle, as well as the crust. So these are basically the various strata of earth. Now why do we have to study all these strata? Because to understand the propagation of seismic wave across various layers of the earth, what we have to do is we have to know what earth is composed of, right? What are the layers of that? So what we find is the inner core and the outer core. The outer core is basically molten, and the mantle and crust are solid forms. So that makes a lot of difference in the propagation of seismic waves across the body of the earth. Sorry, I got an admit request. Let me add a person. Okay. So yeah, so there comes the importance of seismology. Seismology is again a science that deals with the internal structure of the earth, the propagation, the origin and propagation of seismic waves. Right now, we have the globe, we have the earth in the present form at the right corner of the slide. This is the earth in its present form. But how was the earth the same millions of years ago? No. So basically, the origin of earthquakes, or the very existence of earthquakes is related to the collision, or related to the movement of continents between themselves. So that theory is basically summed up as continental drift theory. So millions of years ago, the entire landmass of earth was accumulated into a mass called Gondwana land. I'm sorry, I'm getting a request again. Okay. Yeah. So the entire landmass of the earth is concentrated into a small mass called Gondwana land. The Gondwana land, the continents of the Gondwana land started drifting from each other and formed the what is known as Pangaea. Pangaea is a form of the earth that existed 200 million years ago in the late Triassic era. Okay, so the Gondwana land, from Gondwana land we have this Pangaea, and from Pangaea the continents further drifted apart, and we have what is the present form of earth on the right corner of the slide. Right now, why do these continents drift? Okay, drift apart each other. So we have basically three modes of energy transfer. One is conduction, the other is radiation, another is convection. Right. So as I mentioned, that the mantle and outer core of the earth is molten, and the crust and the inner core is rigid. Right. So what happens is, because of the molten nature, there are some convection currents that are developed in the mantle, right? And these convection currents either push the crust apart, or they pull the crust apart. So what happens is, because of that push and pull, the continents move either towards each other, or they keep moving away from each other. Right, so that is the basis of continental drift. That is why continents keep drifting apart from each other. Okay, so yeah, this is what the left is a visualization of how the continental drift take place, and on the right hand side is a schematic representation of the convective current that is formed. Right now, what is now this continental drift is related to the plate tectonics. What does plate tectonics suggest? Plate tectonics suggests that the entire crustal mass of the earth is fragmented into a number of parts, and these parts are referred to as tectonic plates. Right, so we have around, see, these black lines on the globe are the divisions of tectonic plates we have. So it is observed that there are around 54 plates. Of that 54 plates, there are 7 major plates and a number of minor plates, right? And the number of plates are increasing day by day because of more and more earthquakes that are occurring. Okay, fine. Oh, I'm sorry, I'm getting admit requests and I have to admit everybody. So that is the delay. Okay. So that is what. So uh, we have around 54 plate tectonics. 54 tectonic plates. I guess my slides are not being shared. Okay, thank you. Okay, so the Earth is composed of a lot of fragments, and these fragments, like we see the orange on the right, so the orange peel is separated from the orange mass. Similarly, these crustal mass, it's called lithosphere. The crust and the upper mantle are collectively called lithosphere. So lithosphere sort of floats on the molten mantle mass. So because of that, we have all these plates: Pacific plate, North American plate, South American plate. We have Indian plate and the Eurasian plate. So the plate of our concern is the Indian plate because it is subducting, it is moving under the Eurasian plate. So that is the reason of earthquakes basically in India. Okay. So this shows a slide on, I'm sorry, I'm getting admit requests again. Yeah, so we identify around 54 plates. Of that, seven are major and a number of minor plates, and the number of major plates are increasing day by day. Major and minor plates are increasing day by day. So these plate tectonics, yeah. So now, how do we identify the plate tectonics, and what was the origin of these plate tectonics? We find, if we map all the earthquakes that occurred between 1900 and 2017, we find that earthquakes don't occur at every nook and corner of the world. Instead, they occur at specific locations, right? You can see there is a trend in the location of earthquakes. So this is the trend of all the earthquakes. So when we analyze this trend, we found that the earthquakes occur along some boundaries. These are the boundaries. So that is how the plate tectonics came into origin. The theory of plate tectonics. So the idea of tectonic plates comes from the earthquakes that have occurred in the past, right? Now, we have tectonic plates, right? Now, how these tectonic plates interact with each other, right? We have three type of interaction, basically: convergent boundary, divergent boundary, and transform boundary. Convergent boundary is a destructive boundary because the crustal mass is eaten up, and one crustal mass, one tectonic plate sinks below the other. So it destructs some crust. Divergent boundary, the masses drift apart from each other, right? And we have a new crustal mass that is formed. That is what is called divergent boundary. And transform boundary is a boundary where a slip occurs between the plate tectonics. So these may not be important from civil engineering point of view, but all these interactions and all the waves, seismic waves, and all those seismological parameters are very much required when we do a design for earthquake resistant, when we do incorporate seismic resistance into buildings. So seismology plays a vital role there. So that is why we have to be clear of all these things. Now, why does earthquake occurs? So if we say, if we define an earthquake is a sudden rupture of Earth's mass beneath the ground, right? So what we see is that over time, the tectonic plates on the Earth, they accumulate a lot of strain energy. the strain energy keeps accumulating and accumulating and accumulating, and there is a stress change. There is a change in the stress profile. You can see the because of the stress changes, there are some strain developed between the tectonic plates, and uh, when the strain exceeds the level of the bearing strain, right? The elastic strain exceeds the capacity of the mass, then it explodes with an energy, enormous release of energy. That is shown in the third figure. So first, there is a fault, there is a plate tectonic, and there is a stress development across the plate tectonics, and because of the stress accumulation exceeding a certain limit, there is a sudden release of energy, and we call that as earthquakes. So we have this schematic representation. We have a fence here, and there are stresses acting on this block, and the fence changes its shape, and when, because of the pressure, before the movement of plate tectonics, there is a sudden release of energy that is occurring, and because of that, what happens is the energy is released with a very huge magnitude, and we call that as earthquakes. You can see a blast here. So on this one, this is how an earthquake is occurring because of elastic. This theory is called elastic rebound theory, where the elastic strain energy stored is released gradually. Right now, we'll talk about some terminology of an earthquake. So this is the focus. Focus is the point on beneath the earth where the rupture, where they basically the rupture. You can see this figure. There is a rupture that is occurring, right? Rupture in between the plate tectonics, or a collision of plate tectonics, you can say. That point is called focus, right? And the point exactly above the focus on the ground is what we call as epicenter. So if we follow media reports, we could find that an earthquake of particular magnitude occurred at the epicenter. So basically, epicenter is the point where the maximum impact of an earthquake is basically felt, right? So yeah. Now, any questions still here? Okay, I guess there are no questions. Just to confirm, am I audible yet? Am I audible clearly?
Yes, yes, yes.
Okay, thank you. Now, coming to earthquake waves. So, earthquake energy is basically emanated from the deep beneath the earth's surface to the top of the earth in terms of waves. So, we have a lot of seismic waves, and we classify seismic wave into body wave and surface wave. So, body wave are the waves that travel through the body of the earth, and surface wave are the waves that travel along the surface of the earth. So, what we have here is a ripple. A stone falls on the surface of water, and there are ripples that are formed, and the stone drops down also, right? Through the body of water. So the pressure, the waves that are developed downwards in the direction of movement of the stone is called body wave, and the ripples that are seen on the surface of water are called the surface wave. So that is the basic difference between a body wave and a surface wave. uh, I guess my slides are not yet visible. Yeah, okay. So this is body wave. Body wave is basically the wave that travels through the body of the earth, to the mass of the earth, and surface wave are produced on the surface of the earth. So body wave, what we can classify body wave is, we can classify body wave into P wave and S wave, and surface wave we can classify as Rayleigh wave and Love wave. So if you see this figure also, this is the earthquake source, and from source to the top, the waves travel through the body of the earth, and that is why it is called the body wave. And when it reaches the surface, or when it is about to reach the surface, there are waves in the form of ripples that are formed. So these ripples are called the surface wave. So that is what it happens. So basically, from earthquake engineering point of view, we are more interested in surface wave, because buildings are on the surface and they hit the buildings horizontally. In seismic design, we never consider horizontal forces until and unless we are carrying out an earthquake resistant design. So in the general design procedures do not incorporate horizontal loads in them. So the surface wave are the waves that hit the buildings horizontally. This is very important for earthquake engineers or civil engineers basically. So that is why we have to study a surface wave in much detail. Right now, I said body wave has P and S wave, right? So P wave is called primary wave or longitudinal wave, right? It can travel through the body of the earth. It can travel through any medium. It can travel through solid, liquid and gaseous medium as well. So if we see how this P wave propagates, we have a video here, animated video. So we see that this is the direction of propagation of the wave, and the particles are also moving to and fro in the direction of propagation of the wave, right? So this is what the P wave is. So from beneath bottom of the earth till bottom at a point below the earth till the surface, there are compactions and rarefactions of earth's mass, and these waves reach the surface of the earth, and the direction of propagation and direction of particle motion are same. Now S wave, what happens is the difference between S and P wave. S wave is also called secondary wave or shear wave. Why S wave is called secondary? Because it is secondary to reach. First wave that reaches the ground is the P wave, body wave, P wave, and after P wave comes the S wave, right? So S wave, what is the direction of propagation of S wave is perpendicular to the direction of, for example, S wave is propagating in this direction, then the particle motion occurs perpendicular to that, either horizontally or vertically, like this figure. So this is the propagation of the wave. The velocity of propagation is this direction, but the particles move perpendicular to that. So this is speciality of S wave. Now if you look into the animation, we see that, see, the wave is propagating horizontally in one direction, but the particle is moving vertically up and down, right, or horizontally up and down. Anything can happen. That's why S wave, we have S wave, S horizontal and S vertical. If you could see, there are two parts: horizontal S wave and vertical S wave. So this is what is S wave. Now P wave and S wave are done, and they are body waves. Now coming to surface wave. Surface wave are two parts: one is Rayleigh wave and the other is love wave. If we see the Rayleigh wave, we have elliptical particle motion. The direction of propagation is this, but the particles move in an elliptical fashion, right? As you could see from the video, elliptical motion. So this is a Rayleigh wave and it is a surface wave. Now love wave. This wave is coined after the name A.E.H. Love, Professor A.E.H. Love, and according to him, love wave are the waves that occur because of interference between S and P waves, and there are some specific conditions for the love wave to develop. I think that discussion is beyond the scope of this session. So yeah, still, but love wave is the most destructive seismic wave known to us. Right now, if you see the propagation of love wave, that is similar to the propagation of S wave, but it incorporates both the properties of P wave, S wave together. So if you could classify the waves on the basis of the severity, we would say love wave are the number one severe, most severe, followed by Rayleigh wave, right? Followed by S wave and then P wave. P wave is the least dangerous wave. Now, if we could see, this is a graph of amplitude and time. We see that P waves are the first wave to arrive, and S wave arrives after a span of around 2 minutes, 1 to 2 minutes after the arrival of P wave. And also the P waves are not damaging enough. It is just the S wave that damages, S wave or other surface wave that are damaging, right? Yeah. We could use this reaction time between the P wave arrival time and S wave arrival time for giving warnings. Some instrument can record P waves, right? And whenever the instrument can record P waves, we can sound a warning to people, and people can evacuate to safe places before S wave actually comes and hits. Because S wave is basically more dangerous than P waves. P waves will not harm us, right? Yeah. Now, as I mentioned, P wave is a body wave and can travel through any portion of the earth. So you can see that the P waves are those in blue, right? They can travel in crust, mantle, and core. And mantle is molten. It can travel through molten. It can travel through liquids, everything. But you can see that S wave, the waves in the green, are only concentrated on the upper mantle, and not in the core. The outer core is basically molten. So the P wave can travel only through the mantle and crust, right? No, sorry, the S wave can travel through only hard rigid surfaces like crust and upper mantle, but the P wave can travel through anything, but S wave can only travel through rigid masses. So this is what this figure represents. Now we can see that outer core is molten. If you could see from the figure, as outer core is molten, then we have a zero velocity. If you see the velocities, yeah, this is the velocity, right? So this is the S wave. So S wave velocity is basically zero in the outer core, but P wave velocity never turns to zero. This is the P wave, and the velocities profile is shown there, right? So the P wave velocity never turned to zero, right? Yeah, so that is basically the propagation of Earth. Now, coming to how to measure an earthquake. So the instrument that we use for measuring an earthquake is called the seismograph. Seismograph is an instrument that works on the principle of inertia. As you could know, like most of us would be like familiar with that. Indeed, all of us. So seismograph is an instrument that is used for basically measuring an earthquake. So what we have here, this is a setup, and we have very heavy mass. This fixed mass is very heavy, and when an earthquake hits, the bottom plate moves, the entire setup moves, but the heavy mass, because of inertia, it stays in its position. And because of this staying at its position, it can sketch the signature of an earthquake on a paper, right? So this instrument entirely is called the seismograph. Now coming to seismograph, seismogram. Now this paper is the record of the earthquake. The paper is the record of the earthquake, and if we unfold it, this is a seismograph record is called seismogram. The signature of earth that we obtain is called seismogram, and if we unfurl it, we have this profile. So here also we can see that initially the amplitude is the maximum displacement the wave the earthquake is causing. So initially we have a very less amplitude. So if you can see that P wave here, it has a very less amplitude, and the S wave has a very high amplitude, and it keeps on increasing. So we can see that body waves are less damaging in amplitude point of view as well. First thing, they have caused only vertical movement, and vertical movements are not dangerous for buildings because we have already considered factor of safety for columns, beams, and slabs for vertical loads, right? But for horizontal labs, we do not consider factor of safeties for horizontal loads basically. So, but surface wave also cause a horizontal movement. So surface wave are indeed dangerous. Also, surface wave have a larger amplitude compared to the body wave, right? So that is an important thing. Now, yeah, so that is about the basic of seismology. I'm sorry. Now, I would like to make a point here. The very frequent earthquakes in Delhi region is very much discussed now. So, as seismologists and earthquake engineers, do we really have to be very much concerned about the seismic activity that is occurring of late in Delhi? I would say no, because Delhi region is basically experiencing seismic activity since long time, and none of the recent earthquakes are having a magnitude greater than 4. So magnitude less than 4 earthquakes occur very frequently, and they do not basically cause any harm. So also because of the lockdown, because of coronavirus, it is more perceived by the people, and that's why people are much more scared of that. So Delhi seismicity and the North Indian seismicity in the recent in 2020, there is nothing to worry about, right? But uh, as an earthquake engineer, we must be aware of the fact that Delhi falls in Yamuna basin, and a basin is basically very much attractive site for an earthquake. So it can cause higher damage. One thing is because it is a basin area. Another thing, that Delhi is a very much populated city, so we have to be very careful about earthquakes there, right? So the effects of the earthquake would get amplified in Delhi if at all a big earthquake hits Delhi. The small earthquakes that are occurring now are not much relevant, right? So yeah, so this was the first part of my presentation, and I would take some questions now. So anybody has a question, then please either unmute yourself and ask, or put in the chat box. It'll take a while to listen to some of them. Yes, please. Come on, you can be interactive. Can be interactive. Any doubt, that any clarification or anything?
Student.
Yes, yes, sir.
Okay, continue.
Hello sir, what is Richter scale? How it will be measured?
Yes, yes, yes.
Usually,
Yes, come on. Yeah, that's a good question. So, my friend asked about the Richter scale. So, what we have is, could you follow the slides? What we have is, this is the earthquake signature, and it records the amplitude of ground vibration, right? So, what we do is we measure the maximum amplitude of ground vibration. That is this one. From this point to this point, this is the maximum amplitude of ground vibrations, and this basically occurs in microns only, because but to read it, to record it, we will amplify, and we will take it on a larger scale. So what we do, we measure this distance from here to here in microns, and we take a logarithm of that distance, logarithm to the base 10 of maximum ground amplitude. That is what is called Richter magnitude. So basically, Richter magnitude is the amount of is the correlation of an energy released during an earthquake. More the energy, more the ground vibration. So from the seismograph record, we measure the maximum displacement, and we take a logarithm to the base 10, and that gives us magnitude in Richter scale. Richter scale is the most commonly adopted scale, but there are other scales of measuring earthquakes as well. We have body wave magnitude, we have surface wave magnitude, we have local magnitude, we have moment magnitude, and so on. Media and the local public is more comfortable with the Richter magnitude, but as engineers, we should be more worried about, we basically I mean, scale earthquakes on the basis of moment magnitude, that shows how much seismic moment is generated because of that event. Yeah, so any more questions now? I guess I was clear with that Richter scale.
yes sir.
Okay, thank you, Vijay Kumar. Now, Bharti, you were about to tell something.
Actually, I was saying like students to ask question without any hesitation. Maybe your doubt will be silly only, but it's okay. You are learning new topics, so it is always welcome. And that's it only. Thank you.
Please, no harm. Anybody can ask any questions. There's no harm. It's a new subject, so yeah, basically, please. Okay, so I guess there are no questions as of now. So if at all you have any questions, then please feel free to post them in the chat section. So let's continue with the slides again. Okay. Okay, so that is the earthquake signature we have. So from these, this earthquake signature is the most relevant link between seismology and earthquake engineering, because the signature, the maximum amplitude from this signature is extracted to calculate the magnitude, earthquake magnitude, and that is of very much importance to civil engineers and earthquake engineers. Now let's slowly shift from seismology to structural dynamics. So we all hit the gym. So if we have, like, if you hold the dumbbells in that fashion, the dumbbell is hitting us vertically, and the load is not changing with time, right? That is fixed, right? So that loading is called static loading. And when we lift up the dumbbell, or we do some exercise with the dumbbells, we are imparting some dynamic loading into our arms, right? So because the load is varying with time, so anything that varies with time, uh, either the magnitude of the load, magnitude, direction, or the response of the load, anything, if it varies with time, we call it as dynamic loading, else we call it as static loading. So as civil engineers, basically we would be more interested in doing a static analysis, basically, until and unless we consider earthquake loading. We design buildings for static loads, not dynamic load. But if we shift from basic civil engineering to earthquake resistant design, we incorporate dynamic loads on the buildings, right? And dynamic loads could be because of earthquake, could be because of wind, could be because of tsunami, or could be because of other reasons as well, right? So like we have the tall story buildings, Burj Khalifa in Dubai. Because of wind, the building can sway. Okay, it is made to sway actually because of the wind. So that is also a dynamic loading, and we have to consider that as well. I got another admit request. Okay, right. Yeah. So this is the basic of static loading and dynamic loading part. Now, as I mentioned, a static load is a load which which is not time dependent. Okay, so it does not vary with time. So if we see the graph on the left, we can see that if we plot a force with respect to time, we find that a static load remains constant throughout. When the time changes, there is no variation in the load. The load also remains constant. So that is mathematically what is a static load, right? Now, coming to dynamic load is a load which varies with time. Okay, so if you could see, dynamic loading can be divided into periodic and non-periodic loading, right? So periodic is a type of loading which repeats itself after a fixed time interval. So this is the time interval, and the load repeats itself. So this is called periodic loading. This is also a periodic load. And non-periodic is there is no period, right? Okay, so what we get is, this is because of an impact loading, for example a bomb blast or something. So we get an impact loading, and this is an earthquake loading is again non-periodic. Now how we define a dynamic load? Any load whose direction, magnitude, or position vector varies with time, that load becomes a dynamic load, right? Now, I guess a lot of civil engineers here would be interested in degrees of freedom, and they would be very much well aware of that. Well, if we have, uh, I'm sorry, I'm getting another admit request. Okay, cool. Yeah, okay. Uh, yeah, so we have, for example, we have a fixed support here, and we have four masses connected by rigid bodies, rigid links, okay? And wait, yeah, I'm getting continuous admit requests. Okay, okay. So again, I would welcome the newcomers. So Yeah, coming to the degrees of freedom, how do we define degrees of freedom? Degrees of freedom is basically defined as a number of displacement components to be considered in order to represent the effects of all the significant forces. So to sum it up, basically we have four masses here, right? And because of an earthquake, this mass is earthquakes cause only horizontal loading. So because of an earthquake, the mass at the bottom is allowed to move only in a horizontal direction. So this mass has 1 degree of freedom in translational degree of freedom. We are currently ignoring the vertical movement and the twisting movement. So we say that because of earthquake, this mass has only 1 degree of freedom. Similarly, this mass has another 1 degree of freedom. So we have four masses here, and we have what is called a 4 degree of freedom system. This is a 4 degree of freedom system because there are four masses lumped in this model. Now coming to here there are three masses. All the three masses have 1 degree of freedom in the horizontal direction subjected to earthquake loading conditions, and we have a 3 degree of freedom system here. And here we have a 2 degree of freedom system because there are two masses, and here we have 1 degree of freedom system because there is only one mass lumped at that position, right? So it is very much difficult to analyze a multi-degree of freedom system. So this is a 4, 3 and 2. So all these degree of freedom other than one is called multi-degree of freedom system, and degree of freedom of a single mass or a single degree of freedom system is called SDOF system or single degree of freedom system. So what we do to analyze is we convert a multi-degree of freedom system to a single degree of freedom system. There are some basic approximations or basic procedures to convert a multi-degree of freedom system to a single degree of freedom system, right? So now coming to a little bit technical part. So we have a beam here, right? And we put some static load onto the onto that building, onto that beam, right? Okay. Okay, we put a static load onto that beam, right? That load is not varying with time. So because of the static load, there is no inertia that is developed in the beam, right? But when we excite the beam dynamically, dynamic excitation means we change the load with respect to time. Here the load is constant throughout the application process, but here with every fraction of second or every time, like with every change in time, the loading is keeping on changing, right? Because of the changing in load, we get some inertial forces that oppose the change, right? So we have inertial forces at all the points. So there are infinite number of points on this beam, right? Here we see that wherever there are masses, wherever there are discrete points, we have 1 degree of freedom. But here we see that because of the dynamic load, there are a lot of changes at almost every point in the length of the beam, right? So we call this as infinite degree of freedom system because there are infinite number of small points and that can move in vertical direction, right? So what we do to and doing an analysis of an infinite degree of freedom system is really tough, even though we have a computational advantage nowadays. So what we do is we try to convert this multi-degree of freedom system, that is infinite degree of freedom system, to a finite degree of freedom system. So what we do is we apply the principle of lumped masses. So what we do is we accumulate masses at certain places. So masses around here are accumulated as m1, masses around here are accumulated as m2, and masses around here are accumulated as m3. So infinite points are now constrained to 3 points with lumped masses and equivalent masses, right? So here if we convert a multi-degree of freedom, infinite degree of freedom system to single degree of freedom system, we can run a better analysis. So for example, this building is basically there is a mass at this floor level, roof level, there is a accumulated mass at this roof level, and there is a accumulated mass at this roof level, this floor level. So what we do is we add up all the masses here and we lump it. So here we have a mass, At this floor level, we add up all the masses and we lump it here. So we have another mass here. And at this floor level also, we lump all the masses and we have a mass here, right? So this is a lumped mass system consisting of 3 degrees of freedom. So to analyze a building, three-story building seismically, we apply this procedure. So if it's a 4-story building, there'll be a 4 degree of freedom system. If it's a 5-story building, there'll be 5 degree of freedom system, and so on, right? But anyhow, infinite degrees of freedom is not acceptable. So we similarly we lump masses and convert into 3 degree of freedom system. Now, everybody of us would be aware of what an inertia is. I'm sorry, I got an admit request again. Okay. Okay. So basically, inertia is a tendency of a body to remain in a state of rest or of uniform motion, right? So what happens is, uh, when a building, this is a building and it is subjected to an earthquake loading, so what happens is the building tends to remain in its equilibrium position as before because of its inertia. So you can see that the top of the building sways left while the bottom of the building has to move right because of the earthquake loading. So what the principle of inertia teaches us, and the D'Alembert principle says, is that the external load, the time dependent external load, is equal to the rate of change of momentum, right? This the external load is acting from left to right, and this inertial load acts in the opposite direction. So these are equal. This left to right and this right to left are equal in magnitude. So what D'Alembert principle says that the magnitude of the time varying force is dependent on the rate of change, is equal to the rate of change of momentum. Now, if we simplify that, we find that if we simplify this, we find that rate of change, the external loading is equal to mass times the acceleration. Acceleration is again time dependent. So mass times the acceleration of the body, right? So this is called inertial force. This equation is of importance when we are solving for dynamic problems, right? So this is the inertia force. Now, damping force. Damping is basically a loss of energy. Like we run bikes, we drive cars. So all those have dampers attached. Bikes have shock absorbers. Trucks have leaf springs, and cars have suspensions. What the effect of all those is to reduce the to generate a loss of energy and to help us reducing the vibrations, right? We can travel in a safe mode. So that is what a damping, the significance of damping is. So basically it is a loss of energy which reduces, restricts, or prevents oscillation. So basically, to come to tell it mathematically or graphically, we have the initial amplitude as this much, right? And as the time propagates, the amplitude goes on amplitude goes on decreasing and decreasing. So what we say is a damping is achieved. A damping in the amplitude is achieved here, and after a due course of time, the wave is hardly perceivable, right? So this is called damping. Now, in earthquake engineering, we are more interested in velocity proportional damping because that gets easier to solve. And as an analogy, we presume that the damping that a building has is velocity proportional damping. So the damping force because of viscous damping is F equal to C into X dot. This is velocity, and C is damping coefficient. So this gives us the damping force. So we got the inertia force here, we got the damping force here. Now this is a viscous damper, very much equivalent to a shock absorber in motorcycles, right? Yeah. Now, stiffness force. Now, all of us would be aware of what stiffness is. Stiffness is basically the rigidity of a structural element. So, if we say mathematically, stiffness is the force required to cause 1 unit of deformation. Okay, so that is what stiffness means. So, stiffness K, we call it K, is a force required to cause a unit deformation, right? So, and this force is called stiffness force. So what we have is, now we have inertia force, we have a stiffness force, we have a viscous force also. So these three are the forces. So even if there is no extra extra damper attached to a building, but the building has its own damping from its materials, so we have to consider all those forces. Now we will talk about the derivation of basic dynamic equation. So this is basically a single degree of freedom system because it has only one lumped mass, and we put some earthquake excitation on this single degree of freedom system, and this system bends like a cantilever, vertical cantilever, with a horizontal deformation of delta x, right? Now this system has a stiffness, this system has a mass, and this system has a damping. So what we do is we carry out a spring mass damper analogy for this single degree of freedom system, and we have something called this, something like this. So we have a mass, the entire stiffness is equivalent to a stiffness of a spring, and the entire damping in this system is equivalent to the damping of a damper. This is called a dashpot viscous damper, right? So now this loading, this external load or the earthquake excitation has to be equal to the sum of the inertia force because of this mass, the damping force because of this damper, and the spring force because of this spring stiffener, right? So what we have is that the left hand side, the loading from left to right is equivalent to or equal to sum of all these loads. Just a second. Yeah. Okay. Okay. So this earthquake excitation external force is a sum of spring force plus the viscous force plus the inertia force, right? So inertia force is Fi of t, it varies with time, that is mass times acceleration, and the damping force is we assume it's a velocity proportional damping, and that is c into x dot of t, c into velocity with respect to time, and spring force is again k is a stiffness, constant stiffness, and k into x. So this is the basic dynamic equation. Okay, so yeah, this is the basic dynamic equation for a just a second, I'm getting another admit request. Yeah. So this equation is called the basic dynamic equation for a forced vibration. Now let me tell you what a forced vibration is. Now this is a single degree of freedom, and there is a load acting on this mass, right? And this load keeps varying with time, but that load does not go away. It is there in the system throughout. So the system is forced to move under this load. That is called forced vibration. Now free vibration is something that you put an initial load to a structure, initial load to this degree of freedom system, and you remove the loading. Now after you remove the loading, the system still keeps on vibrating for some time, some more time. So it is now free to vibrate. There is no external agency that is forcing it to vibrate. So that condition is called a free vibration, right? So this version of basic dynamic equation is for forced vibration, we have, because we have an external excitation here. Now if this external excitation is removed after initial loading, we don't have any external excitation, so we put left hand side of this equation as 0, 0 equal to this one. Okay, yeah. So so the left hand side of the equation changes to 0 and the right hand side remains intact. So that would be the equation for basic dynamic equation for uh, a free vibration, right? Here this is for forced vibration. Yeah, now from this we do a free body diagram. So this is the free body diagram. The excitation force is acting this direction, the spring force from right to left, inertia force from right to left, and damping force from right to left. So that is the derivation of this basic dynamic equation, right? Now we do not have just single degree of freedom systems in our surroundings. What we have is basically multiple degree of freedoms, right? So multiple degree of freedom means multiple masses, multiple stiffnesses, and multiple dampers, right? So if we have four stiffnesses here, for example, this is a multi degree of freedom system, 4 degree of freedom system, and we have four stiffnesses because of all these four columns. Now if we want to convert this or to deal with the system, we have to calculate an effective system, effective stiffness. So there is a mistake in this equation. This should be 1 by k effective. So 1 by k effective equal to 1 by k1 plus 1 by k2 plus 1 by k3 plus 1 by k4. So this is the effective stiffness for this. Now this is stiffnesses in series. Now we come to stiffnesses in parallel. Now when stiffnesses are in parallel, we have to just add them up. So that is how we get the effective stiffnesses, right? Okay. So yeah, I'll take a break here, and I would stop for some questions from the audience. If you got some questions, please unmute yourself and please. Yes, Vijay Kumar sir.
Hello, sir.
Yes, sir.
Sir, in the damping force graph, you shown that initial amplitude, but the structure initially it is at rest. How you got that initial amplitude?
Which one, sir? Just a second.
In the damping
Okay, let me go to the damping slide. This one?
The initial amplitude that I not.
See. Because damping is there is damping in this structure. So for example, we are starting from this may not be time 0, this may be time 4 second or 5 second when the vibration has started. So we have just taken a crop of this graph after 4 seconds or 5 seconds of the vibration, and just see, like at 4 seconds, say we have y0 is the initial amplitude of the wave. Okay, amplitude, not wave, amplitude of movement actually. So at 4 seconds, say the movement is the amplitude is this much. After at 5 seconds the amplitude has decreased, and after 6 seconds, see, the amplitude is going on decreasing, right? Even if it is time 0, there could be an initial, because that is amplitude means you're moving. For example, you take this vertical cantilever and you pull this vertical cantilever towards your left, okay, and that you're incorporating a strain in that, delta x strain. So because of this, there is a predefined amplitude into that. So that is how this shows. So after that, because of this damper, the amplitude keeps on decreasing and decreasing. So I guess I am clear, Vijay Kumar sir.
Okay, sir.
Okay, fine. So yeah, any more questions, please? Okay, I guess I'll proceed. Okay, so we have all these forces. We have inertia force, we have damping force, we have stiffness force, and we derive the basic dynamic equation for free and forced vibrations as well. Now, huh, yeah, now this is a question to the audience. Now we have a 20-story building and a 4-story building, right? On my left side is a building of 20 story, and on my right side is a building of only 4 stories. Now, say a hypothetical earthquake occurs in this scenario on a 20-story building as well as on a 4-story building. So which building would shake more? The 20-story building or the 4-story building? So that's an open question to the audience. So according to the audience, which building is expected to shake more? Can either anybody please comment, or either you can chat, put in the chat screen, the 20-story building or the 4-story? Yes, Vijay Kumar says 4-story, Bharti Misal says 4-story. Okay, so yeah, basically 4-story buildings shakes more. What do you mean, like, huh? Okay, so Vijay Kumar and Bharti say 4-story buildings shake more during an earthquake, right? Okay. So what we see here is that is not that much deterministic. We cannot say for sure that a 4-story building can shake more or a 20-story building can shake more, because every building has its own time period. The time period is the time required to complete one set of oscillation, okay, from neutral towards the left, and then to neutral towards the right, and then to neutral, back to neutral. So that entire time is called time period. So depending on the length of the building, the time period of the building changes. So as a rule of thumb, if we have a 20-story building, if we have an n-story building, the time period of the building will be n by 10. So here we have a 20-story building. So that to find the time period, we divide it by 10. So we have 2 seconds for this 20-story building, and for this 4-story building we do 4 by 10. So we have 0.4 seconds for this building. Now, to say whether any building would shake or not, we should comply with the resonance condition, right? So what a resonance condition is says that, for example, an earthquake with a time period of 2 seconds hits, then this building has also a time period of 2 seconds, and there will be maximum shaking in this building because of resonance. Okay, but because of the earthquake of time period 2 seconds, there won't be much shaking in a building of time period equal to this is natural time period, 0.4 second. Building will not suffer much shaking. On the other hand, if the earthquake has a time period of 4.4 second, and that time period of 0.4 seconds matches with the natural time period 0.4 second of the building, then there will be a resonance condition in this building, right? And because of this resonance, this building being a shorter one, 4-story building being a shorter one, undergoes more shaking compared to a tall story building. Now this can be shown using a video. Here I have a video clip here. So we see that the central building is the tallest building. This is the building frame, and this left hand one and the right hand one are small shorter buildings. So as a layman, if I would ask anyone, so they would say because of an earthquake a tall building is supposed to suffer more damage, right? As a layman. Uh-huh. As a yeah, a tall building is supposed to face more damage, but that is not the case, because the damage is basically caused by resonance, and that depends on the natural time period of the building. If the natural time period of the building matches with the time period of the earthquake, then there is a resonance condition, there will be maximum shaking, right? So this is an equation for the time period, 2 pi root of mass effective by stiffness effective. So if I play this video, we can just observe the central building and the other two building frames basically. So yeah, the earthquake, I guess there is some glitch. Okay, I guess somebody else is presenting. Okay, yeah, right. Now, yeah, just observe the central building and the buildings surrounding that. If I play this video, we see that now the tall building is shaking more, right? Yeah. Now just observe the tall building. The tall building is shaking more because the tall building is shaking more now initially because the time period of the tall building is high. So initially we are giving shaking the ground only slowly. Slowly means more time period. So that more time period, the higher time period matches with the resonating time period or natural time period of this tall building, and that is why the tall building is moving vigorously initially, right? So now if we go further into this video, now the tall building is moving vigorously, right? Because the excitation is having a low time period. Now what we do is we we decrease the time period, we make it more frequent. Now we see the shorter building moves faster, the shorter building moves faster, this shorter building has a lesser time period, right? Yeah, so that is what so yeah, again I'll play that. So yeah, taller here, the taller building is moving vigorously, but the shorter buildings are not. But when I increase the frequency of ground vibration, that frequency matches with the frequency of the short buildings, and the short buildings start vibrating vigorously than compared to the tall building, right? So coming as an answer to the question, let me admit somebody. Yeah, okay. Now yeah. Now, which building would shake more? Yes, the answer is the earthquake has to decide which building it has to shake more, either the 20-story building or 4-story building. Everything is a play of the natural frequencies and natural time period also. So in 1960 Chile earthquake, what happened was all those buildings with 21 stories, only those buildings with the 21 story got damaged. All other buildings were not damaged. That is because the frequency of the building, or the time period of the building, matched with the frequency, the natural frequency of, or natural time period of the building matched with the time period or the frequency of the earthquake, and there was a resonance. So only 21-story building were in resonance, other buildings were not in resonance, and only 21-story building were damaged in 1960 Chile earthquake, right? So that was the thing. Yeah. Now this is the equation for time period of a building: 2 pi root mass effective by K effective. Now, okay, okay. Let's do a problem. If all of you have I mean, a pen and a paper with you, or also a calculator, then let's find out the time period of this building, right? So what we can do is, yeah, the mass, this building has a mass this much. The building has stiffness K1 and K2 of this much. Now we are asked to find what the time period of this building is. So this stiffness and this stiffness are in parallel, and to find the effective stiffness, what we have to do is we have to just do a sum of K1 and K2, right? So 0.875, so it will be 1.75 into 10 power 4. That will be the effective stiffness. Now if you calculate, we will get the time period of the building as 0.45 seconds, right? 0.45 seconds. So it will be around a building of a 4-story building or something similar to that, this building. So entire mass I have lumped here, right? So because of that, so yeah. So this is the, and how do we calculate time period? We calculate it using this formula: 2 pi root of m effective by K effective. We get 0.45 seconds here. Now yeah, now what is of paramount importance to earthquake engineers is the estimation of base shear. Base shear is the maximum expected lateral force that the building is subjected to during an earthquake event. The maximum horizontal force. For example, see, all those individual stories from first story till 10th story is subjected to seismic loads, and that is increasing. The highest story will have highest seismic loading, expected lateral force, okay? And if we take a sum of all these lateral force, we get something called as base shear. Base shear is the sum of all these lateral forces, right? Now yeah, with the, when we get the time period of the building, we can actually calculate the total base shear, okay? I'll show you how. And after we get the total base shear of a building, we have to distribute the base shear into various individual members. So we have F1 base shear of entire base shear has to be transferred to this member, this member, and this member, right? So the horizontal loading is now incorporated, and we can design our members for these horizontal loads. So using this equation, these equations are available in IS codes, maybe 1893. Yeah. Now this is the building that we have taken, and we have a time period of 0.45 seconds, and this building is located at Pune, and this building is a special moment resisting frame, and it's a residential building. Now we have to calculate the base shear. Now we see that the time period of this building is 0.45 second and located at Pune. Now Pune, I am sorry, I did not add the seismic zoning map. Pune let me talk about that a bit. India is basically zoned into 5 seismic zones, right? Zone 1, zone 2, zone 3, India is basically zoned into 4 seismic zones: zone 2, zone 3, zone 4, and zone 5. Earlier there we had 5 zones, but then zone 1 was considered to be least earlier it was considered to be least earthquake prone, but there were some earthquakes in zone 1 as well. So in the later modification of IS 1893 zone 1 was merged with zone 2. So now we have zone 2, zone 3, zone 4, and zone 5. All the Himalayan states are where I am now in Assam, and I am in a zone 5 area. So all those Himalayan states northeastern states, all those states are located in zone 5 and they are exceptionally prone to earthquakes. Talking about Pune, Pune comes in zone 5. Sorry, Pune comes in zone 4. Why? Because there is an intraplate or reservoir induced seismicity because of its Pune is near to Koyna Dam, and because of Koyna Dam, there are a lot of chances, because Koyna Dam is responsible for the earthquake, largest magnitude earthquake caused because of a dam. Around 6 magnitude of earthquake was caused because of Koyna Dam. So as Pune is very near to Koyna Dam, Pune is classified into zone 4 basically, but other parts of Maharashtra are very come in zone 3 and zone 2 respectively basically. So Pune, because it's proximity to Koyna Dam, we call it, we assign a seismic zone factor of 4 to Pune. Now if you take IS code for a building which is in zone 4, we consider higher Z factor. Z factor is a factor which depends on the seismic proneness, earthquake proneness. Okay. Yeah, so we consider Z factor. So for Pune we have 0.24. So to calculate if this building is in Pune, we use Z as 0.24 here. Now I is the importance factor. Now again, if you go for this one, IS code, coming to the importance factor, table number 6, we have if it's a hospital building, school building, or a public building, we have an importance factor of 1.5. But this being a residential building, the importance factor for this building is only 1.0, right? Now coming to the response reduction factor. Now I have mentioned that this is a special moment resisting frame. Now what is a special moment resisting frame? A special moment resisting frame is a frame, right, which is developed by adopting all ductile detailing provisions as per IS code 13920. If we do all those ductile detailing for that building members, then we call that the building is a special moment resisting frame, right? So for an SMRF building, if we take IS code table number 7, we find that special moment resisting frame, we can take a response reduction factor R of 5.0, right? So in this equation, Z we put as 0.24 because this is in Pune and zone 4, and I importance factor of 1 because this is a residential building, and R is the response reduction factor, we take it as 5. And SA by G is something we get from a chart called uh, yeah, we have this one. I guess I have not mentioned about that. Okay, fine. That SA by G is basically obtained from response spectrum. Okay, response spectrum is also available in the codal provisions. And first we what we do is, and a response spectrum chart is there, and that chart is depends on the time period of the building. So 0.4 for a building of time period 0.45 second, we get the value of SA by G. So that we have just to substitute. Now how that response this the chart is obtained is the chart has been obtained by what collection of a lot of details from the past earthquakes response spectrum. Okay, so that is how we interpolate that graphically, and that is how we have a this one response spectrum, and from that response spectrum we get SA by G for the particular T value. Now if I take the SA by G value from the chart, I get it at 2.5. Now coming to entire equation, up to SA by G, this base shear equation is dimensionless. We multiply this dimensionless equation with the seismic weight here, right? Now Z by 2 into I by R into SA by G into the seismic weight. So we get the base shear for this building as 5.327 kilonewton, right? Now this base shear of 5.327 kilonewton is a total base shear that we have, and that can be distributed to individual members. So Fi is this into this, and here multiplied by base shear. Okay, Vb, I missed that. So if you do that, we can get the individual horizontal forces that this system is subjected to. Right now, talking about this was a numerical part. Now how to control damping. So I would present a few methods which have been used globally to control the vibration. So first is tuned mass damper. So this is a damper, a heavy mass that is hung from the top of a building and allowed to move. So this mass is tuned according to the frequency that the building could be subjected to. So what happens is when an earthquake hits, this mass goes in resonance with the frequency. The frequency of this pendulum mass goes in almost in resonance with the frequency of the ground earthquake, and it takes up all the vibrations, and the building does not vibrate. It's the mass that vibrates inside, but the building does not vibrate. This is a schematic view of a tune mass damper in Taipei 101 tower. Okay, and this is the inner view of this damper. So using a tune mass damper, we can achieve some damping in the building, and we can safeguard the building, right? Another is base isolation. So if we have this foundation, this is a rigid foundation, and the building is resting on that, and because of whenever an earthquake strikes, this building moves to and fro, right? And there is an interstory drift. The drift at this story is not same as the drift of this story, is not the same as the drift of this story. So the drift changes between stories, and there is a relative difference in the interstory drifts here, right? And because of that, there are some shear forces that are developing at various joints and various members of the building. Now what we do is, for example, instead of this rigid support, we place a roller here. So after we place a roller, what happens is, because of the earthquake, the building moves in unison. It will move together. When it moves together, there is no difference in the interstory drift. Everything will seem to be parallel, similar to this. So what happens is, there is no additional shear forces that are developed in this building, and that is how it could safeguard our structure. So but if we place a roller, the horizontal movement of the building will be uncontrollable. So what we do is, we use a this one we use some viscoelastic material or something sort of that. Maybe this is a plate of rubber and steel, stitched towards each other, or melted or welded within each other, and we use that. And because of that, the entire building, this actually fails also, but after it fails, we can actually work on it, and we can change this also. So because of that, the entire building moves together in unison, and there is a reduction in the interstory drift that is obtained. So this seismic isolation, this base isolation structure, a lot of buildings are using that, and in India, Bhuj hospital has used this seismic base isolation after the 2002 Bhuj incident. Also we have an example of tune mass damper in India, and that is this statue of Unity in Gujarat, that uses this tune mass damper inside. So yeah, so these are two of the vibration control devices that we have here. Yeah, so yeah, so basically that is there. And I guess I am at the end of the presentation now, so I would open like this venue for the questions there. So if anybody has questions, please post either in the chat or can ask me personally by unmuting yourself. Please, I am open to questions now. Bharti, I could not catch you. There was some technical glitch from your side. Your internet is weak, I guess. Could you please try to repeat?
Actually, I was asking to
Okay, fine.
participants that to ask questions
Yeah.
regarding any terminology implementation that's been understood.
Okay. Yeah, please feel free to ask any queries here. I guess a lot of the members, a lot of our friends are. Yes. I guess a lot of our friends are new to this topic, so maybe they have this initial trouble. But it's an interesting topic. Anybody can take up structural dynamics and earthquake. It's basically an interdisciplinary topic, which incorporates a lot of ideas from physics, from structural dynamics, from all this basic structures, everything, basic civil engineering, everything is there incorporated in this. So yeah, please go ahead with some questions if you have.
I think the best question I have usually like the maximum it is if you have any questions regarding the same.
Okay. Yeah, Bharti, you were not clear again. Like, could you repeat? Your net is lagging. I could not catch you.
Okay, so I wanted to ask for a little bit concluded to a student from V. Hello.
Misalia, could you please text that? I think your network connectivity is bad. Can you please elaborate what is the main factor we need to take
All
into
these
consideration?
students must understand that this is your syllabus topic, and here basic part is that you must understood the earthquake, how it is propagating, what are the yeah. Mr. Nazil Sabah,
Yeah.
one question is there from faculty that can you please elaborate what is the main factor we need to take into consideration to avoid the earthquake damage in the construction?
Right. So, sir, yeah. So, Professor Bhane, sir, so I got your question. So, basically, what are the factors that are taken into consideration to avoid earthquake damage is proper engineered construction, I would say. So, starting from the geotechnical investigation, because first we have to do a micro zonation study of the area. So we have to find what is a soil type. Some soil types are basically damp the earthquake vibration, as well as some soil types basically amplify some the ground vibration. So first we have to identify what is the underlying soil type, what is the topography over there. For example, it's a basin area, then we can expect a higher amplitude of wave. So that one first, and then we have to take the zoning into consideration, and with that we can estimate the maximum ground acceleration that could be produced there. So basically what we have to do is we have to construct a building with all those guidelines, right? Complying with earthquake resistant design. So we have to use this IS 1893 1893, and we have to calculate the base shear for the building properly, and we have to do all those. Also we have to do ductile detailing for that building properly. So well engineered building is the answer to the factors that is considered to safeguard a building from earthquake. So what we do is, another thing I would like to mention is we have to reduce the risk. So what for earthquake engineers, life is what it counts. Even if a building is damaged slightly, what we design, what our design expectation is, we design a building in such a way that the building does not collapse. Okay, it is allowed to experience minor cracks, minor damage in structural as well as non-structural members, but it does not collapse and fall on the people. So basically in earthquake philosophy, what we do is we try to reduce the risk. So what is risk? If we mathematically produce what is risk, then risk is hazard into vulnerability into exposure. Hazard is the underlying proneness to the earthquake. For example, Pune is in zone 4, Assam is in zone 5. So that is the hazard, right? And vulnerability is how we take steps to tackle those buildings. Like, for example, if I have my residential building, I need not invest crores and crores to make it 100% earthquake resistant. I can actually entertain some sorts of cracking in the building, but I will make sure that the building does not fall on me or collapse on me. So that is how we achieve economy. But if it's a hospital building, what I have to do is I have to take more and more parameters and to make it more and more earthquake resistant. It should not shake also much, because some surgeon would be performing a surgery inside, so he should also not be disturbed. So we have to invest more income, more economy into that, right? So basically we are reducing the vulnerability. So that is the main aim of that has to be considered in reducing the earthquake damage. And risk is hazard times vulnerability times exposure. Exposure is the underlying conditions there. So we don't have any hold on hazard and exposure. We can only control the vulnerability. So to make a building more and more vulnerable, now how about all those existing buildings? We can strengthen those buildings. That is called seismic retrofitting. So we can strengthen those buildings so that they can actually survive better in earthquakes. So yeah, so all those points have to be taken into consideration. And for a country like India, yes, we have to go for severe earthquake planning, earthquake resistant design for buildings, and that would be the need of the hour. And countries like Japan have come out with buildings called Sky Tree and all, which guarantee 100% seismic resistance. So yeah, so that is what. So any more questions, please?
From what? Okay. Thank you, Vanessa, for the question and for the answer. After that, I request the students to break it down. Okay. One more question is there from Karnita, that when we are going to use seismic coefficient method and response spectrum method, which factor we consider on priority basis?
Okay, basically what we use is a response spectrum method because that is little more advanced than seismic coefficient method. Also, now the shift is moving towards performance based seismic design and risk targeted seismic design. So basically seismic coefficient method is slowly getting outdated, and all those codal provisions like IS 1893 or the European codes or American codes all are inclined towards response spectrum method more. So I guess that would be the need of the hour. And also response spectrum method is getting outdated, and we are coming with performance based design and risk targeted seismic design. So basically I'm not the one who's working in a structural design sort of thing. I basically work on seismology and interrelate seismology with earthquake engineering. That is my domain. So I may not be the right person to judge like which one could be better. But yeah, we are shifting from seismic coefficient method to response spectrum method, and further we will be moving on to performance based seismic design and risk targeted seismic design. That is the answer.
Okay. Thank you, Kandirisa, for the question. And Mr. Najib, I think student might not know the what is meant by seismic method and all, but as to proceed into the today was only the introduction session where you the requirement was you must know what is meant by more was that you must understand the dynamic equation. We just must the wild like the going on. Okay. I think we must stop questioning.
Yeah. Yeah, so this topic is basically an interesting one, and I request everybody to go through certain interesting topics of earthquake engineering, and that would you can actually take it as your part of your career, multidisciplinary research, and all. It's possible. There are a lot of opportunities open in this discipline, so yeah, you can actually carry on for that. So, Bharti, I guess there are no more questions,
Say
right?
something about this. Yeah, that's why only I'm saying. Pradeep, it's over to you now.
Yes, ma'am.
Okay.
Thank you, sir. Your session is very useful to us. I would like to say thanks to Bharti ma'am and Nikam sir to arranging this seminar to us. This seminar increases the interest of students in earthquake. And, thank you, sir, for giving very important time to us.
Okay.
Thank you, sir.
Thank you, Pradeep sir. So it was nice interacting to all of you, and I actually thank Sri Ramchandra College of Engineering Pune for giving me this opportunity to interact with all of you and share my limited knowledge with you. So yeah, thanks a lot for that as well.
One more thing I want to note that at the end of this session, one PPT will be shared. Means today's PPT, whatever was discussion, will be shared. You take note this very carefully, all students.
Ma'am, your voice is not clear.
Okay. Sorry for the disturbance. Now, am I audible properly?
Yes, you are.
Yes, ma'am.
Okay. From Civil Department, from Sri Ramchandra College of Engineering, I would like to thank our HOD sir for attending and organizing, basically giving us freedom to organize such a session for the benefit of students. Our Nikam sir, then our faculty members like Kankiri sir was there, Patil sir, then Hatre ma'am, Rupali ma'am, Pandey sir, and all other faculties from the Sri Ramchandra College of Engineering was present for the session. Our academic dean, Dr. Sujata Rao ma'am was there, and not but our students from third year, second year, and final year was there present. And last but not the least, our speaker, Mr. Nazil Sabaha, have delivered a beautiful session where I hope all participants understood what is meant by earthquake, how it is proceeding, and what are the future scope of this subject. I feel like today also I am in MTech class only as we used to do in our MTech period. So hope you will find one I can say out of it, so that at least one student can take earthquake engineering as his or her future. So with due permission of HOD sir, can I end here, sir? Hello, HOD sir. Hello. My voice is audible or not?
Yes, ma'am.
Okay.
Actually, sir, not in.
Okay, maybe due to some network issue, he is disconnected now. So I would like to invite our senior faculty member, that is Patil sir, to say something from HOD sir's point of view. I hope he is there. He is not there. I think he is also disconnected or what. Kangiri sir, you want to please?
Yes, ma'am.
Yeah, sure, sir.
Nadir sir, first of all, your presentation was very nice. Very neatly you have explained each and everything in detail.
Thank you, sir.
So that was the very impressive.
Thank
and the way you given the answer for the question, it was very nice. And as earthquake related faculty, so you have more knowledge than us. So we got we learned from you very much, what you can say, new thing we learned from you today's session, and it is very helpful to our students for their future betterment. Thank you, sir.
Okay.
The session was very nice. Thank you.
Thank you, sir. Thank you, sir, for all the support.
Thank you,
Yes.
Okay. I would like to address another point. Yeah, that was I was about to ask you only. Okay.
Yes.
Yes, ma'am.
So first of all, my congratulations to the Department of Civil Engineering for organizing very practical session, earthquake and remedy and structural design. Really, the session was the last 15 minutes. I'm sitting in the session only. It was very interactive session, and the speaker is holding the patience to answer all the questions from the faculties and the students. Thank you on behalf of the Shriram Sudhir College of Engineering. So exactly, I don't know the name of the speaker, but thank you, sir, for your patience listening to our questions and answering. And once again, congratulations to the Department of Civil Engineering and all dear participants. Thank you.
Thanks a lot, ma'am,
Thank you,
for your
ma'am.
sincere comments. Thank you.
Actually, I want to say his name is Mr. Nazil Sabah, ma'am.
Yes, sir. Yes, yes.
Okay. Thank you, ma'am, for your feedback. With this note, I would like to end up this session for today. Hope on feedback forms we will get idea about that whether we will continue these sessions for in future also. Okay. Shall we?
Yes,
with
please.
the permission of all the faculties, I will say that this is our ending portion of our session. Okay.
Ma'am, please send the feedback link here also.
Yeah. Okay. I will
If
share.
possible.
Okay. So may I log out now? I guess that's the end. And thank you everybody for being a patient
Share
listener.
with all of you. Okay. Thank you all.
Okay.
Okay.
Okay. I am
Yeah,
disconnecting.
thank you.
Thank you. Okay. Bye. Have a good day.
Okay, sir. Okay.
Yeah,
Thank
Okay.
you.
Okay.
Yeah.